The purpose of this presentation is to discuss buffer systems and how we can perform pH calculations on acid-base buffer systems. First thing we need to know about buffers is that essentially a buffer is a system that resists changes in pH when small amounts of acid and base are added. Buffers generally require the presence of a weak acid-base pair that don't consume each other. And so the easiest way we can do this is to use a conjugate acid-base pair. If we mix two different weak acid, weak base pairs, they may consume each other depending on how their Ka's and Kb's stack up. We can make buffers at pretty much any pH, but they're going to work best whenever the pKa of the acid or base that we use to make the buffer is near to the pH of the buffer system that we want to create. And so I'm going to show you one generic equation to use for an acid buffer. You can modify this to use it for the base buffer if you wish by substituting Kb for Ka, or you can just look and change the Kb to Ka for the base to the acid to introduce this equation. But essentially you can use this anytime a buffer is involved. There is another equation that's on your AP formula sheet and probably also in your textbook that you can use called the Henderson-Hasselbalch equation. However, I'm not going to use that. It's just an expanded or derived version of an equation that's based on what I'm going to show you. And I don't want to cause confusion, so I'm only going to show one way to do it. If you'd like to see the other way to do it, you can come and speak to me in person and we'll work that out for you individually. But the equation I want to show you looks at solving for the H+, the hydrogen ion concentration. And essentially all we've done here is rearrange the Ka expression that we write for weak acids in general. And instead of having Ka equal to some equilibrium expression, we've solved that for the hydrogen ion concentration. So if we look at this, the hydrogen ion concentration, which is where we get pH, depends on two things. It depends on the Ka of the acid, which is inherent to the acid. It's not something that we can modify. And then it also depends on the ratio of acid to conjugate base, which is something that we can manipulate. So we can fine-tune pH and hydrogen ion concentration by manipulating the ratio of acid and base that we see. Another important part of buffers, called buffering capacity, is also controlled by the amounts of conjugate acid or conjugate base and acid present. So once I know the ratio of those two, I can set the capacity just by making those amounts larger. For example, if I need a 1:5 ratio, for example, I could make HA be 0.5 and A minus be 0.1 and have a small buffering capacity. Or to get a relatively larger buffering capacity, I could make HA be 5 and A minus be 1. It's the same ratio, so it will set the same pH, but it will resist much, or will accept much more addition of acid and base before the pH changes noticeably. The best way that if we want to resist changes in either direction is to make the two concentrations equal for my conjugate base and my acid. If that's the case, I can resist a downward movement and an upward movement. However, if I know I'm only going to be looking at systems where, say, I have an upward movement in pH that I want to buffer against, then I can heavy load my system so that I have a lot more of one of the other components to stop that from moving in that direction, if I don't really have to worry about it moving in the positive or negative direction. Okay, so how do we create a buffer? Well, like we said before, buffers are created by adding conjugate acid-base pairs to a solution together. And so when we do this, we need to try to maintain ratios at 1 to 10 or less. This just tends to work better. You can make them outside of this area, but the buffering capacity in the one direction becomes extremely limited. So if we keep them at 1 to 10, we get a little bit better. If they ask us how we would prepare one in a question, the easiest thing to do is to set it up this way and to make one of them be 1 molar. Then you can just make the other one relative to that, and that makes it easy on you to explain how to produce one. Okay, so when making the buffer, we should know what pH we want to make, and so we'll look at the Ka value for the acid portion of the buffer, and that'll help me know which acid would be a good one to make the buffer solution. The Ka of the acid should have an exponent on the same order of magnitude, or very close to the same order of magnitude, as the pH of the buffer I want to produce. So if I want to make a pH 5 buffer, for example, I know acetic acid has a Ka of 1.8 times 10 to the minus 5. That's probably a good choice. Whereas hydrogen sulfate, for example, has a pKa of about 10 to the negative 2. That would not be a good choice to make a pH 5 buffer. If I have pKa's to look at to compare for determining, this is even better. pKa is found in much the same way that pH is. To find pH, you take the negative log of hydrogen ion concentration. Well, to find pKa, you take the negative log of Ka. And so if I have pKa's to look at, then I want to select an acid with a pKa as near as possible to the buffer pH that I want to produce. Another special note about buffer systems: if I add equal amounts of HA and A minus, like we said before, that buffers the best in both directions. That also means that H plus equals Ka, or pH equals pKa. So if I can find a pKa that is equal to the buffer pH that I want to produce, all I have to do is grab that acid and put an equal number of moles of acid and conjugate base in the system, and away we go. So now we want to look at some example problems. The first example we have here asks us to calculate the pH of 0.5 liters of a buffer solution composed of half molar formic acid and 0.7 molar sodium formate, both before and after the addition of 10 milliliters of a strong acid, 1 molar hydrochloric acid. And so some things I need to know about the system. First is that the Ka of formic acid is 1.8 times 10 to the minus 4. That wasn't given in the problem, but I looked that up in a data table so that I would be able to use it. And now we'll apply the equation that was given to us in the beginning. First, we're going to find the hydrogen ion concentration, and when this is before any acid is added. That is equal to 1.8 times 10 to the minus 4 times HA, which is the formic acid, so 0.5 molar HA concentration over A minus concentration. And so when I do that, I'll see that H plus is equal to 1.29 times 10 to the minus 4 molar. And so it's a simple thing here. pH then is equal to the negative log of H plus. So if I take the negative log of 1.29 times 10 to the minus 4, that's a pH of about 3.89. So this, before I add anything, this buffer has a pH of 3.89. Now, if I drop down and look at what happens when I add it, after equilibrium is established, I have some base form. This is formate, and I'm going to add to it a strong acid, hydrochloric acid, which will become H plus in water. And that's going to produce some of my formic acid, HCO2H. That's formic acid. And so essentially I'm going to create an I system, but we're not really thinking of equilibrium here. The strong acid will fully react with this base. So if I look at the fact that I have half of a liter of each of these two solutions together, I can generate what their initial concentrations are. Half a liter of 0.7 molar formate means that I have 0.35 moles of this. I'm going to use 10 milliliters of 1 molar, so that is 0.01 moles. And my formic acid started out at half of 0.5, so 0.25 moles. That's initial. Change, equilibrium. The H plus and the formate are going to react, so this is going to go down by 0.01. This is going to go up by 0.01. Down by 0.01. This will go up by 0.01. And so at equilibrium, I'll have 0.34 moles of formate, 0 moles of excess H plus. There'll be a little bit from the equilibrium, but not enough to worry about. And here we'll have 0.26 moles of the formic acid. And so now it's just a matter of reevaluating my H plus given these new concentrations. Something that's important here to note is that we added to this, we had half of a liter and we added 10 milliliters to it. So my new total volume at equilibrium is going to be 510 milliliters. Just be aware of that. So in this case, H plus is equal to Ka, which is still 1.8 times 10 to the minus 4. That's a property of the acid, does not change. Now my concentrations in this case are going to be slightly different. For the formic acid part, instead of 0.5 molar, I have 0.26 moles located in 0.51 liters. I'm going to divide that by my formate concentration, 0.34 moles, also in 510 milliliters, and I'll see quite readily that those two volumes cancel out, and my new H plus concentration then is 1.38 times 10 to the minus 4. So we've gone up in H plus concentration, which we should, because we've got more formic acid formed, so more will dissociate back in equilibrium. And so the pH then is the negative log of that H plus value, and so we see we have a pH now of 3.86. So we changed some, but not a lot, for adding 10 milliliters of a strong acid, and that's what buffers are supposed to do, resist pH change. Alright, using acetic acid sodium acetate buffer solution, what ratio of conjugate acid to base do I need to maintain a pH of 5? Well, again, things I need to know. The Ka of acetic acid is 1.8 times 10 to the minus 5. I want to operate at a pH of 5, which means that the concentration of H plus equals 1 times 10 to the minus 5, just applying the antilog function. And I also know that if I rearrange my equation here that says H plus equals Ka times concentration of Ha over concentration of A minus, solve that for concentration of Ha over concentration of A minus, that's going to be H plus over Ka, or 1 times 10 to the minus 5 divided by 1.8 times 10 to the minus 5, which happens to be equal to 0.55 repeating. So that means essentially that it's 5/9. So that's the ratio I need to maintain. How would I make such a solution? Well, the first thing I would do, just to be simple, since I know it's 5/9, is I would mass out 0.9 moles of sodium acetate and add to volumetric flask 1 liter with 100 mLs of water. Second thing I would do, find volume of concentrated acetic acid to make 0.5 moles and add to 1 liter flask with the acetate I've already got in there. Step number 3, dilute to 1 liter total volume. And that's how I would make that solution. Alright, very quickly at the bottom, we want to make a solution that's buffered at 4.3, and we want to choose from the following acids for their soluble salts. Looking at these exponents will help me. This one is way off. This is going to be between 7 and 8. This one is on the upside of 3, so this will be between 2 and 3. So really I have a choice to make between these two. Something that's interesting about pH and pKa, because I'm taking negative logs, when I see small numbers like this is 10 to the negative 5, but it's a little bigger than 10 to the negative 5, which means that this will be between 4 and 5, but closer to 5.